Welcome to this first tutorial on programming in Stationeers. Today, we will write a simple but useful program to show what programming is like in Stationeers. We won't go into too many details for now. This is to give you a feel of what it's like. So here we are in our lovely greenhouse. The ferns we grow in here produce oxygen from carbon dioxide for us to breathe. Oxygen production is the basis of our survival here on Vulcan. It allows us not only to breathe, but also to produce fuel and water. There's no water on Vulcan, but there is a lot of carbon dioxide. For this tutorial, we want to use the oxygen in the room to fill our canisters. For that, we use a filtration device to filter out the oxygen and fill a canister. Canisters can be pressurized up to 10 megapascals. Beyond that, they will start to take damage and then explode. Here's a cut scene of what it looks like.
Mission critical. Health critical.
As you can see, this is quite brutal and causes a lot of damage. We definitely do not want that to happen. That's why we need automation, and for that, we need to do some programming. Let's get started. The main device we use is a filtration. Filtration are made from an atmospheric kit, some pipe, and wire. Like that. You can filter up to 2 different gas at the same time. Here, we only want oxygen. So oxygen filter it is. 1 filter is enough. 2 would last longer. For input, we want the gases in the room. To achieve that, we just connect a passive vent to the input connection. The unfiltered gases can return to the room. So, a vent there too. The filtered gas will go to our canister. Using pipes and utilities kit, we can set up a canister storage. Like this. The small reservoir is optional. It allowed to have some gas ready when we insert a canister, speeding up the process. The first step in creating any automation is to understand the process and figure out how to control it. If we turn on the filtration, we can see the pressure build up in the canister by looking at it with an empty hand. It will fill up until it explodes. Let's stop for now. We can also inspect the canister using a tablet with an Atmos analyzer cartridge. Here we have more details. We see that our filtration is working since we have only oxygen in it. We can also see the temperature, pressure, and the quantity in moles. If we point to the filtration device, we don't get much, unless we use a device configuration cartridge. Here, there is a lot to see. We can see that it is off. There is also a lot of information about pressure and various gas ratios. All these are called logic types and can be used in our programs to make decisions and change the states of devices. We can notice that the pressure output logic type matches the pressure in our canister. That makes sense, since they are connected. If we also point to the green display on the device, we can see that the mode is active. That means it will filter gases. By changing the mode, we can have the device on and not filtering. This is convenient, and we will use that in our program. We should also check the online help to learn more about the device we want to control. Let's find the info for our filtration device. The description tells what we just saw together. After that, we have the slot. We see that there are 2 filter slots and a programmable chip slot. That also checks out with what we just saw. Next, we have the modes. Here, 0 is inactive and 1 is active. Then, the list of all logic types for the device. And finally, the connection. With all that, we have a good idea of what we have to do. We want the filtration to be active as long as the pressure is below, let's say 6 megapascals, which is a safe setting. You can go for higher pressure, but keep in mind that pressure will increase if the canister is heated. In order to program our device, Let's insert a programmable chip or IC10 into the device. Then we will need a computer with an editor motherboard in it. Here we go. Notice that we have connected the data port on both the computer and the filtration. This allows devices to communicate. In the top left corner, we can see a menu that allows us to choose which device we want to program. Here, our filtration device is our only choice. On the bottom right, there is the Edit button to open the editor. The first thing we are going to do is rename things. You'll see that this is something we do all the time in programming. It helps us with reasoning and makes our program clearer. We want to control the filtration device. Let's give a name by creating an alias for DB, which is the device our programmable chip is in. That is the filtration device in that case. Next, we want to monitor and control the output pressure and mode of the device. To do that, we need a register to hold these values. There are 16 registers, named R0 to R15. We create aliases for registers to clarify their purpose, helping us implement our logic effectively and avoid mistakes. We also use a name for the maximum pressure using the define instruction. We wanted 6 megapascals, but here we have to write it in kilopascals, so it's 6,000. Now we want to read the output pressure from the filtration. The L or load instruction allows us to read a logic type from a device. As you can see, as I type L, the editor gives me hints about what the instruction needs. It also provides a description when I hover the mouse. This is helpful, especially when you're starting out. After some time, you will know all that. If we read this instruction from right to left, it says, load the logic type PressureOutput from the device filtration into the register pressure. That is, when this line is executed, pressure will hold the output pressure value of the filtration. Next, we want to compare the pressure with the maximum pressure we have defined. For that, we use the store less than instruction, or SLT, for short. If we read the description, it says that it will store, in a register of our choice, 1 if the value of a register is less than the value of another register. Otherwise, it will store 0. This is convenient since we want the mode to be 1, or active, when the pressure is below the maximum pressure, and 0 when it is equal to or above. All that is left to do is to write or store the mode on the device. Again, S is for store. This is our logic. If we run it as it is, it will execute once. What we want to do is continuously monitor the pressure and set the mode accordingly. To do that, we need to create a loop. At the beginning of our logic, we place a label. A label is a name for a line. Yes, we like to give names to everything. We will also add a yield instruction just after it. This allows our program to wait a little before continuing. At the end of our logic, we place a jump or J instruction to the start label, thus creating the loop. Our program is executing line by line, starting at the top. We can use instructions like jump to change its flow. This is it. That should fill our canister up to 6 megapascals, and then put the filtration to idle until we need it again. Let's try it. As the pressure reaches 6 megapascals, our program will change the mode to idle, stopping the filtration. It works. In this introductory tutorial, we've seen that once we've built a contraption and operated it manually, it becomes much easier to identify the logic types required to automate the process. Understanding which devices are involved and the logic types that control them allows us to clearly formulate our program's purpose. In this case, it was simply fill a canister up to a defined pressure. Having such a clear statement about what our program will accomplish is extremely helpful when planning our approach. We began our program by renaming the generic device names, like DB, to more meaningful ones. We also created aliases for the registers that hold the logic types we load from devices, and defined names for any useful values with the define instruction. While this naming step is technically optional, these meaningful names make our code much easier to understand and reduce errors when implementing our logic. Next, we wrote the actual logic. Most automation processes follow a similar pattern. First, we load logic type settings from devices. Then, we perform calculations with these values, such as comparisons. Finally, we store the results back to specific logic types to achieve the desired outcome. Since most processes need constant monitoring, we implemented a control loop that continuously loads, processes, and stores logic types. Labels and branching instructions like jump make this continuous execution possible. That's it for today. I hope this introduction has given you a good first glimpse into programming in Stationeers. We've only scratched the surface, and there's much more to learn. In future tutorials, we'll explore more advanced concepts and techniques that will enable you to create increasingly sophisticated systems. Happy programming, Stationeers!